Hello everyone, welcome to ExamRat. My name is Shatabdi and today I'll be taking up the second lesson for thrust and pressure. Okay, so let's get started. In case you have missed the previous lessons on gravitation, the introduction of buoyancy and all the other chapters, you can easily just go to our channel, you'll get there everything. If there are any doubts or queries that you find after watching the videos, do comment in the comment section below. I'll be happy to solve your doubts. So let's start today's session. Okay, so let's do a quick recap of the previous class, what all we had learned. So thrust and pressure. Okay, so thrust, we had talked about how it is the force applied on a surface perpendicular to the surface, right? So if this is the surface and the force applied perpendicular to it, perpendicular matlab the angle between the force applied and the surface will be 90 degree, okay, or the force applied normal to the wooden block, you can say, like normal or perpendicular. Okay, so that was thrust, perpendicularly applied force. Okay, now we come to pressure. Pressure was also very simple, thrust per unit area. Thrust per unit area. Okay, and we had known that lesser the area of contact, more will be the pressure, right? Because pressure is inversely proportional to area. So the amount will reduce the point of contact or the surface of contact between the force and the surface, more will be the pressure on the surface. We had given an example of a nail and a wooden block and how the nail easily gets pushed into the surface because the area of contact is very less, whereas the wooden block is not able to pierce the surface. It just puts the pressure on it but not enough to be penetrated. Okay. We have learned that the unit of pressure is Pascal. Okay, the law of fluid pressure, it was basically that if an object is placed like fully submerged, then the pressure that the fluid exerts on this object is equal on every part of the object, which means that the fluid will exert an equal amount of pressure on all parts of the object. It is actually same for the container also, like if there's a container also and the fluid is filled in it till the rim, then the fluid will put equal amount of pressure on every molecule of the surface, equal and undiminished. So all parts of this container will receive the same amount of pressure by this fluid contained inside it. Okay. Our last topic of discussion for the previous class was buoyancy. Now what was it? I had told you that whenever you go swimming, the moment you jump on the water, you feel like the water also kind of pushes you up, right? That's why you directly do not sink. You go a bit down and then you come up. And why do you come up? It is because that the water also gives you a push, gives you an upward force. Now this upward force is called buoyancy. Okay. So now the buoyancy or buoyant force, also called upthrust, denoted by U, the letter U. It is the upward force exerted by any fluid upon a body placed in it. So any body that is placed on a fluid will be acted upon by the upward force. Now the magnitude of it will depend upon the weight of the object. Honestly, if it is a very heavy object, then the upward force will not be enough to make the object float or be half immersed. It will literally sink because the weight is very high. But if it is enough so that the upward force or the buoyant force, it balances the weight. Weight equals to, we know it's mg, and if the buoyant force is able to balance the weight, then the body will float or float in a half immersed way. Now, how do we know whether the body will float, whether the body will be half immersed, whether the body will sink? It all basically depends on the Archimedes principle and how Archimedes formulated the way in which we can calculate the amount of upward force or the amount of upthrust experienced by every body on the earth. Okay, so let's talk a bit about Archimedes. Now, who was he? He was basically a Greek mathematician. So in those days, basically, it was monarchy, obviously. So this king had basically asked Archimedes, since he was also a part of his council, the king had asked Archimedes that I have gotten this gold, this huge piece of gold. I want to know how pure it is. So obviously, in those days, there weren't many machines or anything so that we can use them to understand the purity of a substance. So what he did was, like, he accidentally actually formulated the principle because he was just thinking of how to like measure it, and it kind of made him mad. He used to think about it when he used to go to sleep, when he used to eat, when he used to bathe, all the time, 24/7. So it so happened that one day while he was taking a bath, he went into his bathtub, which was full of water, and the moment he sat down, he saw that some water spilled over to the floor. So at that moment, suddenly he had this enlightenment, he had this realization, and he shouted, Eureka! So that is how we relate Archimedes to how he formulated the Archimedes principle. He shouted Eureka, Eureka, and then he went to the king and then he explained what had just happened. So, what exactly happened was that when the moment he sat on the bathtub full of water, an amount of water got displaced, like it fell out of the tub. Now, the reason why he got so excited is because he realized that the amount of water displaced was actually his own body weight, was equivalent to his body weight. So here what is written is that when a body is immersed fully or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. So basically, since he sat down fully, he realized that the amount of displaced water was actually equal to his entire body weight, right? So that is all about Archimedes principle. And now, after realizing this, he then calculated that there can be three cases. Like, not always does every object fully immerse, right? Some objects partially also immerse, and some objects do not immerse at all, they just simply float. So how do you differentiate between these three cases? Okay, so let us first take the case that if the body is fully immersed. So if the body is fully immersed, it's very clear that the buoyant force was not enough to keep the body afloat, which means that the weight of the body here is definitely greater than the buoyant force, right? Okay, so in the case 2, if the body is partially immersed, then what does it mean? Then it means that basically, let's just draw it. So if this is the object, so you're seeing that it is partially immersed, right? Like this portion of the body is immersed. So from here we can understand that obviously some amount of water has been displaced, right, for which this portion of the body could be immersed. So basically the amount of water displaced is equal to the weight of this portion. So how do we calculate it? Okay, so we know Let's say density of water is denoted by sigma. Okay. So now let's say that weight of water displaced weight of water displaced is equals to m into g. Now what is m? M here is, you know that density is equals to mass by volume, or we can write it as m equals to sigma into v. V is the volume of the water displaced. So let's just write it VW. So mg equals to VW into sigma into g, right? So this that we got, the weight of the water displaced, this will be equal to the weight of this portion of the wooden block or whatever the object. Okay, so case 3, if the body floats on the surface of the liquid, here it's very simple. Here W, or the weight of the body, is absolutely equal to the up thrust. So there is no displacement of water, right? Because it is completely floating on the surface. Right? Yeah. So yeah, that is it. And also if the body is fully immersed, I'm sure that you have felt like whenever you're swimming or whenever you're in water for some time, you'll feel a little lighter, right? So now, why do you feel lighter? Like, if you measure your weight at that point of time, you'll realize that it is less than what your actual weight is above the sea level. Like, whenever you're standing or sitting or doing anything above the ground. So basically, you feel lighter because of a weight difference that is created between the weight of your body and the weight of your body inside it, which is basically the weight of your body minus the upthrust force, which basically gives you the apparent weight. Okay, so this is all that you need to know for now. Archimedes principle basically then became very famous, and like it is used nowadays in a lot of things. Like it is used in designing ships and submarines. Um, why is it used? Because obviously submarines are constantly underground, right? So you have to basically adjust the weight of the submarine in such a way that it does not fully sink. It remains in the same state of motion. It continuously floats submerged in the sea, right? So you have to balance the upthrust force and the weight of the body. Um, excuse me. It is also used in lactometer. So what is lactometer? It is used to determine the purity of a sample of milk, and hydrometer is used for determining the density of liquids. So initially that I had told you that Archimedes was given the job of finding the purity of gold. So now you realize that something in its purest form will obviously weigh different than if you mix certain alloys or certain other materials with it. For example, if you take a glass of milk and if you take half a glass of milk and pour remaining half full of water, then obviously the weight of the full glass of milk will differ from the half milk half water glass. So that is the concept. Like that is how lactometers came into use, because it made us realize that how we can calculate the purity, like in this, using the same principle that Archimedes used by the whole displacement method. So yeah. Okay. Coming to the end of the chapter, we'll learn about relative density. It also again has applications in finding out purity of things, in comparing the densities or the purities of two different objects, two metals. Okay. So before relative density, first let's just have a quick recap of density. I'm sure you guys know what it is. It is mass per unit volume, and unit also kg per meter cube. This is the SI unit. We can also write it which is not the SI unit. We can write it as gram per centimeter cube, right? The density of a given substance under specified conditions remains the same. So no matter where the body is, whether it is in oil, whether it is in water, whether it is in air, anywhere, the density of a substance will always remain same. It is one of its characteristic properties. Okay, it cannot change. It is the same thing as mass. Mass can never change, whether you're on the moon, on Neptune, on Earth. Mass of a body will never change. What will change is the weight, because the acceleration due to gravity changes, right? So in the same way, density is also a characteristic property. It will never change. And yeah, what I told you, that also always helps us to determine the purity of a substance. Now, what is relative density? First, let us discuss about the term relative. Relative means, again, comparison. Okay. So, obviously, when we talk about relative density, we mean that we are comparing the density of one object to another, right? So, what we do most, like 99% of the time, is we compare the density of any object with the density of water. So why do we do that? Very simple explanation. The density of water is 1 gram per centimeter cube. So it is very easy for us, like, to divide anything by 1, right? If we would have kept the constant density to be compared to all the objects to be that of gold, then it would have been difficult, because it is different, right? Like, you have to have divided it by 19,300. So instead of that, if we just use water, we just have to, like, divide it by 1000, like 1000 kg per meter cube. So it's simple. Just to keep the calculation simple, we divide it by the density of water. So what is it? It is basically density of a substance divided by density of water. As simple as that. And since it is a ratio, since we are dividing one density by another density, we basically give no unit, because ratios have no unit. So yeah. And now another small thing to observe here is that, okay, let me give you an example. So let there be a block of iron. Okay. So we put it once in a container full of water, H2O, and we immerse it also on a container full of mercury. Now you tell me what will happen in case 1 and case 2. So what's going to happen is that in case 1, the iron will sink. But the funny thing is that the iron will float on mercury. It will not sink. Now, why did this happen? It happened because the relative density of iron with respect to water is greater than 1. And when Rd is greater than 1, the object will sink. But when we compare the density of iron to the density of mercury, we found out that it is less than 1, because the density of mercury is very, very high. Because we know that mercury, the molecules of mercury, their force of cohesion is very, very high. Cohesion means the force of attraction with which one molecule attracts other molecule of the same type. Okay, so since the cohesive force of mercury is so high that it always sticks to each other, it does not let other objects pierce it or penetrate through it. as a result of which, since the density of mercury is very very high, iron balances it somehow, and since the relative density becomes less than 1, it floats on the surface of water. Okay, so all these things you need to know when you are discussing about the pressure, the thrust. They'll give you examples of, like, explain to me how does a hydraulic machine work. Then you have to explain the same thing that I had explained last time in our previous video. If you have not seen it, you can easily just go to our channel and see it. So we had talked about how in a hydraulic machine, this is A1, sorry, A1, this is A2. So, and the whole hydraulic machine here is filled with water, tightly contained here. Yeah. So what's happening is that even if you put a small amount of force here, F1, since the area is very very small, so F1 by A1, since the area is very 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 small, the pressure, the magnitude of pressure is a lot, right? So what happens is that since the area 2 is already so big, to compensate for the immense huge pressure, you will automatically feel a huge force this side. And why is that? That is only to keep this pressure constant. And why is this pressure being constant? Because I told you in some slides before, just yeah, I told you that pressure of a fluid will be undiminished and equal in all directions of the fluid. So even if I had extended this container and attached other container to it so that some fluid went here also, then also all parts of this full container will receive equal amount of pressure at all the points. So in the same way, pressure will remain constant. So this will again be equal to F2 by A2. And to compensate for the large area here, you can very well understand the force that the area 2 feels will have to be huge. And that is the mechanism of a hydraulic machine. Okay. Another thing, just this is the last topic. It is something related to the buoyant force and the pressure inside water that we just talked about. So it's very simple. Let's just take a container here and let this be a cylinder. Okay, this was a bad cylinder. Let me draw a proper one. Okay, so yeah, this is better. Okay, anyway, so yeah, what happens is that whenever you are like immersing it fully, so what is exactly happening? So since you're immersing it, obviously there's a downward force here. Okay, and you know that buoyant force is also present. So like in every fluid there is buoyant force. This is a liquid. So here also the buoyant force will be applied. So now the funny thing is that the downward force here is being applied on area 1, and the buoyant force here is being applied on area 2. Okay, so why are we discussing it here? It is because when you are forcefully immersing it, so you will put the pressure on the top of the cylinder, right? And the cylinder in turn will give you a pressure towards the upside, right? So basically what happens is that a pressure difference is created between this part and this part. So let's just calculate it. So let F1 be mg, okay, and here mg is basically density into volume into g, right? Okay, and also F2 here is again mg okay. So what is going to happen is that since you are putting a force upwards, so the F2 is since F2 is the force exerted by the water, the density here will be that of the water, and the density of F1 will actually be the density of this mass, this object or the cylinder. Okay, let us just write it as O. So basically F1 minus F2 is equal to rho naught Vg minus rho WVg, right? So now this is the force, and what is happening is here, to find the pressure, you know what you'll have to do, you'll have to divide it by the area in question. So now since this is a uniform cylinder, I know it does not look so, but it actually is a uniform cylinder, so the upper part of it is, the area of the upper part is equal to the area of the lower part. So instead of writing A1 and A2, we can write A1 equals to A2 equals to A. So what happens here is we divide it by A. Okay, so now what will happen is, if you divide a volume by its area, then what do you get? You get the height, right? So this here is the height. So basically what we get is, if we take the V as common, so V into rho naught G minus rho WG, right, divided by A, sorry. So here it will give us H G into rho naught minus rho W. So that is all that you need to know for now. It's not that difficult. So by this we come to the end of this chapter of a short introduction on fluid and pressure. So thank you for your patience, and do subscribe, do follow us.